Okay, so this lesson is about solving linear inequalities. I, if you're in that last period class, I will have gone through this first part already. I'm going to post the whole lesson just because I don't know where I'm going to be able to stop. So feel free to go through this at your own pace, and that way you can see kind of what we've talked about. But today, we're going to talk about linear inequalities. Tomorrow, we're going to talk about polynomial inequalities. And so these are our last two lessons of our polynomial functions unit. When you write an inequality symbol between two or more linear expressions, we call that a linear inequality. So by inequality, we mean like a less than or greater than sign. And so often there's not just one correct answer or two correct answers, but we might have a range of correct answers or an interval of correct answers that all fit within the criteria. So if we want to look at which operations preserve the truth, we can check this inequality here. So 4 we know is less than 8. And if we add any number to both sides, so I add 2 and I add 2, in this case, that would give us 6 is less than 10. Well, yeah, that's still true. So this preserves the truth. It's still true. An inequality is still true if we add the same number to both sides. Similarly, if we try subtracting the same number from both sides, so here I tried subtracting 3 and subtracting 3, well, yeah, the left side's still going to be less than the right side. So here it'd give us 1 is less than 5. That's still true because I've decreased both sides by the same amount. Multiplying by positive numbers. So here, as an example, multiplied both sides by 4. Left side we get 16. Right side we get 32. Yeah, still that left side's smaller than the right side because we've scaled them both up by a factor of 4. But the left side started being smaller, it's going to still be smaller. So this is still true. Now if all of a sudden we try multiplying by a negative number, so I multiply by negative 2, I get 4 times negative 2, I get negative 8. 8 times negative 2, I get negative 16. But now negative 8 is greater than negative 16. A smaller negative number is larger, so that switched our inequality. So this no longer preserves that same inequality we started in the beginning. It's no longer a less than sign, it has to switch to a greater than sign. Similarly, for division, if we divide by a positive number, it doesn't change our inequality. But if we divide by a negative number, that is going to change if we it's going to change the direction of our inequality. So 4 was less than 8. Divide both sides by negative 2. Well, now the left side's greater than the right side. So multiplying by a positive or dividing by a positive keeps the inequality pointed the same direction. Multiplying by a negative or dividing by a negative switches that direction. So as we saw above, most operations preserve the truth of the inequality. We had a whole bunch that did. The exception occurs when both sides are multiplied or divided by a negative. And so in these cases, both these cases here, yeah, we had to flip the sign of our inequality to preserve the truth. So keeping this in mind, inequalities, they're going to solve just like an equation. So if we see something like this, 3x minus 1 is less than 8, we're going to solve that pretty much the same way we solve 3x minus 1 equals to 8. So move everything without your variable to one side. So we'll add 1 and add 1. And we get 3x is less than 9. And then isolate our variable. So divide by 3 and divide by 3. And we get, well, x is less than 3. Same as if you solve 3x minus 1 equals 8, you would get x equals 3. And so our solution, it can be represented in one of 3 different ways. So on a number line, using set notation, or using interval notation. So on a number line, we want x to be less than 3. And I actually already messed this up. If we want x to be less than 3, we don't want to include 3. It's not less than or equal to. We're going to put an open circle, not a closed circle. So I've crossed this out. We need an open circle because we don't want to include the 3. And then we'll use our arrow over to all the negative values. So that way it's saying that we go up to 3, but not including 3. Our other two methods are just like how we talked about domain and range in the beginning of this course. So set notation, that's the way of writing like domain and range that we're very familiar with. So x is an element of all real numbers such that x is less than 3. Perfect, we're just kind of popping that inequality into that set notation. And then the interval notation, which is newer for a lot of people, we start with that same thing. So x is an element of, and then we want to write the interval. So you're always going from your lowest value to your highest value. Round brackets mean don't include those numbers, just like an open circle means don't include that number. And we never want to include infinity. So we put a round bracket negative infinity because it can keep going left forever. And then comma 3, that's our maximum part of our interval. And again, a round bracket because we do not want to include 3 in our answer. If we needed a square bracket here, that would reflect a closed circle here. For this question here, we're being told how we're going to express our final answer. So this one says express our answer in set notation. This one says express our answer in interval notation. You do have to know both. So you want to be careful. What is the question actually asking you to use? But we're going to keep solving the same way. So isolate your variable, solve it like a linear equation. There's just a couple small things to be careful about. So here I subtracted 35, and I subtracted 35, and we just get left with our negative 2x is greater than or equal to negative 15. And now normally, if this was an equal sign, well, I would divide both sides by negative 2. But because I'm dividing by a negative, that means I'm going to have to flip my inequality. And so I flip that inequality. It goes from a greater than or equal to sign to a less than or equal to sign. And then, because I have a negative over a negative, I can just write that as a positive over a positive. So now we need to write this answer in set notation. X is less than or equal to 15 over 2. And so we write it in that standard domain form. Just take this inequality, throw it into your kind of domain forms. We need that x of element of all real numbers. You're saying it's continuous as long as x is less than or equal to 15 over 2. For our second question here, I multiplied both sides by 5. So that gets rid of the fraction on the left. Everything gets multiplied by 5 on the right. And so now we have an option. You could bring the x's over to the left side. You're going to get a negative. And you could deal with it the same way we dealt with this one here. Or just bring your x's over to the right. And then we can go forward from there. And so divide both sides by 4. So 7 is less than or equal to x, which really that just means that that big opening has to go towards your x. So x is greater than or equal to 7. These are the same expression, same inequality, just written with everything flipped over. So now we want to express our answer in interval notation. We have a greater than or equal to sign, which means we need a square bracket, and we put our low value and our high value. So we start at 7, we go up to infinity, so we keep going forever, and this would be how we'd write this answer in interval notation. So on the back side of the page, we can also do this graphically as well. So we have a linear equation is greater than a linear equation. So let's try graphing these two lines separately. So a y equals 2x plus 2 and a y equals 4x plus 8. So graphing our first line, we have a y-intercept of 2, and we have a slope of 2, so over 1 up 2, over 1 up 2. We can draw this line on here. And our second equation has a y-intercept of 8 and a slope of 4, so over 1 unit, up 4 units every single time. And so we can draw this purple graph here, y equals 4x plus 8. So now, if we're trying to figure out, well, where is our red graph greater than our purple graph, we have to look at the same x values. So we have to look vertically. And so if we look up and down a straight line, we want to see which one's above. Is it the red graph or the purple graph? So right here, if I look straight up this line, purple's above red. So that means that my y equals 4x plus 8 is above my y equals 2x plus 2. Now, in order to find out, well, where's the red graph above the purple graph, we're going to have to move our line over here to the left. Here's the point of intersection. And it would appear that everything left of this is going to have that red graph above the purple graph. The red one, if we look straight up and down, is higher than our purple graph. And so I've shaded in this area to help maybe make it more clear. But we can also check, okay, does this make sense algebraically, the answer that we said? So it looks like starting at -3, going to the left, the red graph should be higher than the purple graph. So solving this inequality, I subtracted 2 from both sides, brought this 4x over, so I just subtract 4x, we get -2x is greater than 6. And then if I got to divide by -2, my sign's got to flip, and I get x is less than -3. And that's what we had talked about here. At -3, they cross. Everything to the left is where that red function is greater than that purple function. So yeah, it looks like algebraically we've proven the same thing as we did on this graph. For this second question, I've put it into a format that's easier to graph, so multiplied out our -2, -6x plus 20, that's kind of in our mx plus b form. 2 times 3x plus 4, we get 6x plus 8, that's in our mx plus b form. So let's graph these two equations here. So we have our one function with a y-intercept of 20 and a slope of -6, and a y-intercept of 8 and a slope of +6. And we want to know, when is this function less than or equal to this function. So again, we have our point of intersection right here, right at x equals 1. Well, either it's going to be the left side or the right side, because they're straight lines. Once they cross, they're never going to come back on each other. If we look to the right here, yeah, all the straight lines up and down here, this function is less than or equal to this function's y value. And so I've shaded this area here to the right. And because it was a less than or equal to, we can represent that as x is greater than or equal to, because they're equal at 1, but x is greater than or equal to 1. So let's see algebraically if we get the same answer here. So here, we had already done that multiplication up here, but I showed it again just so I could start off with the same original equation. Add 6x and add 6x to both sides. Bring that 8 over, so subtract 8. Divide both sides by +12. And then 1 is less than or equal to x is the same as x is greater than or equal to 1. And that's exactly what we had talked about on our graph here. So the very last thing we're going to talk about here, we have these compound inequalities. So this means we really have like two inequality symbols happening, or more than one, I guess I should say, inequality symbols happening at once. So we have 30 is less than or equal to this whole part here, 3 times 2x plus 4 minus 2x plus 1. And this was less than or equal to 46. And so we can split that into like two separate ideas. We have our left inequality. So that's what we've written here. And if I cover up this in the original, the right inequality, this middle part, is less than or equal to 46. And that's what we've written right here. And so really we just have two inequalities we're going to try to solve here all at once. And so we can expand out our brackets. 3 times 2x plus 4, we get 6x plus 12. Minus 2 times x plus 1, we get minus 2x minus 2. Collect our x's. 6x minus 2x is 4x. 12 minus 2 is 10. Subtract 10, we get 20. And then divide both sides by 4. And write it as an inequality with x on the left, because that maybe makes more sense for how we read it. We're going to get x is greater than or equal to 5. For our second inequality, well, expanding the brackets gives us the same terms. This time we're less than or equal to 46. Collect your x's, you get 4x. Again, we get 10. Subtract that, we get 36. And then if we divide both sides by 4, we get x has to be less than or equal to 9. So both of these need to be true if this whole inequality, both these inequalities were true in the first place. So let's look at writing our answer on a number line, and then I'm also going to talk about set notation and interval notation as well here. For the number line, I'm going to use big closed circles at 5 and 9 because I want to include those values. We can be equal to 5 or equal to 9, and then it's just we're filling in that number line between the two things. So yeah, we're everything from 5 to 9, including 5 and 9. In our set notation, this might look familiar. 5 is less than or equal to x, which is less than or equal to 9. So kind of like our minimum value and our maximum value, and x is in between them. And yeah, of course we need less than or equal to symbols because we want to include 5 and 9. And then with our interval notation, again, yeah, we want to include 5 and 9. So we're going to put square brackets and our lowest value and our highest value. So we have our 3 different methods to express this inequality. One more question here. So let's take a look at this one. So I can look at the first part of this inequality. 2x plus 4 is less than 5x minus 11. Subtract 2x, subtract 2x, I get 3x. Add 11 to both sides, we get 15. Divide by 5, and then rewrite it with our variable on the left. We get x is greater than 5. And for our right inequality, so using these two things, 5x minus 11 is less than or equal to 4x plus 3. Subtract 4x, add 11, and we get x is less than or equal to 14. So again, we have two different conditions, and we want to try to combine that into a number line, and I'll show the set notation and interval notation as well. So at 5 and 14, I've put those two dots on here, and I don't want to include 5, so I've left that one open. I do want to include 14 because we could be equal to 14, so I've filled that one in, and now we can just fill in the space between those 2 points. And so we get something that looks like this. And then for set notation and interval notation, we want to make sure we are not including 5. So 5 is less than x, but we are including 14. So x is less than or equal to 14. Same with set notation. We want a round bracket, so we don't include 5, and a square bracket, so we do include 14. These methods, again, you always have your lowest value and your highest value in order both times, no matter which way you've written it, because we have like a lower bound and an upper bound. So this lesson, this is meant to be an introduction to this idea of how do we deal with inequalities. So that biggest thing is that if you had a negative, you have to flip your inequality. Other than that, the solving is very, very similar to equations. It's just that the way we can express our answer, instead of just writing x equals something, we have a few different ways that we can express our answers. So careful to flip your inequalities, solve it like an equation, and make sure you read how your answers to be expressed here. Today is very much a warm-up. We're trying to get used to these inequalities, and so we talk about linear inequalities first. Tomorrow we're going to talk about polynomial inequalities, which are a little bit more involved, but how can we still solve something like that? So let me know if there's any questions at all, please. We have one more lesson tomorrow, and then we're all done the polynomial functions unit. So Friday we have review. You have the weekend to study. Review is already posted for you to take a look at, and our test is on Monday. Let me know if I can help. All right. Have a good day.